Okay. It's recording that and not this, right? Yeah. Recording, it says I'm screen sharing. Well, we'll find out. This is our test round, right? Um, okay. So I wanted to review first what we talked about the last class, especially since you guys didn't have homework. So we have this curve. I'm going to call this the function f. And if we wanted to calculate the average rate of change of the function over a closed interval, so meaning over an interval, an x interval, we wanted to know at what rate y was changing with respect to x on average. We would do that by calculating the slope of the secant line. So I'm going to call the endpoints of that interval x and x plus h, where the length of that interval would be h. So x corresponds to the point x comma f of x. And then x plus h corresponds to the point x plus h comma f of x plus h. And then there's 2 points. So the line that would pass through those 2 points, we call a secant line. When we want to calculate average rate of change over the interval from x to x plus h, that's the same thing as calculating the slope of the secant line. And if we do that just for the general function, so using the general function, like we basically come up with a formula that allows us to calculate the average rate of change over any interval on the function's domain. So just thinking slope formula, right? Change in y over change in x, that looks like f of x plus h minus f of x, that would be the change in y, over x plus h minus x. And that denominator will always end up simplifying to be h. Okay, it will always end up simplifying to be h. This is also called the difference quotient. And you can find the difference quotient for any given function and use it as a formula for calculating average rate of change over an interval, which would be thinking about how the dependent variable is changing with respect to how the independent variable is changing over that interval. So like we were looking, that graph that we started with that was about COVID data, right? We calculated the average rate at which the daily number of cases was increasing by. The number of new daily COVID-19 cases was increasing by. And I think we came up with the interval of time that we were looking at initially, we looked at and said the number of daily cases was increasing by 500 cases per day over the interval that we were examining. Now, let's say that we wanted to calculate the rate of change at a point, not over an interval, but at a point. Like if we wanted to calculate the rate of change at the point x comma f of x, we talked about being able to estimate that rate of change by making h smaller and smaller. Like you could think about choosing values for x that would make the interval smaller and smaller. Like if you drew a secant line, let's say from there to there, right? That would be a more accurate representation of the rate of change at x comma f of x than our original secant line, right? Our original slope. Or if we chose, here, I'll use a different color, a point even closer. Right? The slope of that secant line would be even more accurate. But we're thinking about making h, which is the length of the interval that you're calculating average rate of change over, smaller and smaller and smaller. Where you're like, oh, that seems like a limit. The idea of a limit, h approaching 0. So basically, we can come up with our formula for calculating instantaneous rate of change. Which is the rate of change at a point by thinking about taking the limit of that difference quotient, right? Finding the slope of the tangent line. I call that M tan. So that's the limit as h approaches 0 of our difference quotient, f of x plus h minus f of x all over h. And we call this formula that we can come up with for any function, we call it the derivative. So M tan, that can also be representing, you can think of it as f prime or y prime, depending on the notation you're using. So this is our derivative. One thing we didn't talk about is if you wanted kind of a shortcut for calculating the slope of the tangent line at a given point, like you know what x is, you can just plug in. Like let's say that you wanted to calculate the slope of the tangent line at c comma f of c. The way that you could do that is just do f prime of c, which would be the limit as h approaches 0 of f of c plus h minus f of c all over h. And there's an alternative form of this that we'll discuss later in this section. But if you wanted to come up with the general formula, so the general, like the derivative of the function, leave it as x, and then you could still calculate f prime of c later by just plugging in c. But for when we're talking about differentiability, for certain functions we're going to examine, it's going to be easier to plug in that x value because we're going to talk about differentiability at specific points. Sophia. It's notation that indicates that the rule represents the derivative, that the formula represents the derivative. And by using f prime, you know that that's the derivative of the function f. Like g prime would be the derivative of the function you've named g. So it demonstrates because you might be dealing with multiple functions, multiple derivatives. If all of them are y equals and you're using y prime or dy over dx for all of those equations, like that's where it gets really confusing, like which derivative goes with which function. So using function notation can be really handy and is necessary at times. Okay, so this class left off at our actual examples. We talked about these 3 different notations that you should be familiar with. So we just talked about F prime or G prime, H prime, K prime. If it's y equals, you can either, so if the function that you're dealing with is y equals, you can either use y prime or you can use dy over dx or dy over dt if the independent variable is t, in order to represent the derivative. You have those 2 options, but if function notation is being used, you should use the F prime notation. So we want to find the derivative of this quadratic, and we're using the limit definition. A lot of you guys probably know already that there are shortcuts for finding the derivative. Like there's pretty straightforward rules that we can use. We're going through this lesson for this assignment. You have to earn the right to use those shortcuts. So you have to use the rule for this assignment. You have to use the limit definition of the derivative. I get it. It's painful. But especially for some of these functions, being able to discuss differentiability, it's going to be necessary. Okay, so to find the derivative of this function, you can either use dy over dx or you can use y prime to indicate that we're finding the derivative. And this is important. Don't just have the limit written there without stating what it represents. This is y prime, or you can use dy over dx. But that's going to be equal to the limit as h approaches 0 of our difference quotient. And our difference quotient in this case, we're first thinking about replacing the x's with x plus h. And then subtracting the function. So I'm going to use some sort of grouping symbol. So I'm going to use brackets since I've already used some parentheses there. But to subtract the original function. And then that's all over h. And if you remembered the last time when we talked about finding the difference quotient for a function, and we did an actual example, I was like, okay, once we've set this up, this is our difference quotient. You can technically use this to calculate average rate of change, but we're thinking about where we're going. We want to get this h to cancel. We want to use algebra. Now, looking at this, we're taking a limit. What would happen if you use direct substitution and plug 0 in for h? What would happen? What would happen? No. Indeterminate form, you would run into 0 over 0. And guess what? Anytime you're using the limit definition of the derivative, that's going to happen. There's going to be algebra that you have to do. Yes.
It wouldn't be 0. Yeah.
It would be 0 over 0, right? Yeah. So in this case, you guys have the tools in your toolbox. What should we do for this limit? How can we try and uncover in the numerator that h that's going to cancel with the h that's in the denominator? Which strategy is this? Colin. I called it sledgehammer, right? Like it's just brute force. We're not multiplying by a version of 1. We're just multiplying everything out and hoping we can get that h to cancel. So after we've done that, so multiply out the numerator. So x squared plus 2xh plus h squared plus 3x plus 3h minus x squared minus 3x I feel like this always ends up being a little bit of like algebra boot camp too, working through this. Like limits and like this, I guess this is still limits, ends up being good algebra practice. Okay, so those x squareds will cancel. The 3x's will cancel. And then notice all the terms that are left in the numerator have an h in them, where we could factor out an h. I'm going to write out that step. We could factor out an h. Then we'd have 2x plus h plus 3 all over h. Woohoo, we got that h to cancel. So once we get that h to cancel, then it's, okay, use direct substitution now. And when we use direct substitution, we would get 2x plus 0 plus 3, or just 2x plus 3. This is our derivative. This is our formula that we can use to calculate the slope of the tangent line to any point on the curve of y equals x squared plus 3x. So no, 2x plus 3 is the derivative that would allow you to calculate the slope of the tangent line to the curve. We'll do an example in a sec where we actually do that. So this is the derivative of y equals to x squared plus 3x. Yeah, this is not the tangent line. I understand why that's confusing since it's linear. This is a slope, or this is the formula. Formula you can use to calculate the slope of the tangent line. Tangent lines. Any questions so far? All right, so next we're going to find dy over dx. We're going to find dy over dx for 1 over x. So dy over dx will be equal to the limit as h approaches 0 of 1 over x plus h minus 1 over x all over h. What happens if you try direct substitution? Indeterminate form. Okay, so which strategy are we going to use to get that h to cancel? Not ratcom, we're not rationalizing. Yeah, we want to get rid of those there's complex fractions. I called this the LCM over LCM because you're thinking about the least common multiple of the numerator and the denominator. Or sorry, you're thinking about the least common multiple of the denominators of the complex fractions. So what version of 1 are we going to multiply by? Over x plus h. Remember, it's multiplying by 1. And it can be helpful to think about putting grouping symbols around your big numerator and your big denominator to indicate that you're going to be distributing, right? We're going to distribute x times the quantity x plus h to each of those fractions in the numerator. So when we do that, we still have our limit notation because we have not used direct substitution yet. The x plus h's will cancel. We'll be left with x. And then minus the x's will cancel and we'll be left with x plus h. Make sure you have your parentheses around the x plus h. And then all over h times x plus h. Remember, don't distribute that h in. We want that h to cancel. You can follow it all the way through. Then we want to distribute that negative. Try and uncover that h that we're trying to get to cancel with the h in the denominator. So what? We would end up with negative h over h times x plus h. So this h will cancel with this h. Yay, we've done it. And if we use direct substitution, we would end up with negative 1 over x times x plus 0. Well, that just simplifies to be negative 1 over x squared. So this is our derivative. This is the formula that we can use to calculate slopes of tangent lines to the curve 1 over x. Is it okay to move on, you guys? You know what's funny? Anytime I share my screen on Zoom or anytime I record, I think it says 9:41 a.m. Oh, and it's Tuesday, January 9th. Isn't that strange? Are you sharing messages, Justin?
No, just.
Gotcha. You guys just going ahead? I know that some of you guys have done this already before. It's review. Okay. Same type of question. We're finding f prime for the function f of x equals to the square root of x, but we're actually going to use f prime this time. So f prime will be equal to the limit, as h approaches 0 of our difference quotient, which would be the square root of x plus h minus the square root of x all over h. If you try direct substitution, you get 0 over 0. So this is one where we would want to use retcon. So we want to rationalize the numerator to try and uncover that h that's going to cancel with the h in the denominator. So the square root of x plus h plus the square root of x over itself. So that would end up being x plus h minus x all over h times the square root of x plus h. Don't forget that denominator. The x's would cancel. And then you could probably see that h would cancel. I'm going to write it out here. So this h will cancel with this h. Once you've gotten that h to cancel, then you can use direct substitution. So we'd get 1 over the square root of x plus 0 plus the square root of x, which is 1 over 2 root x. Colin, do you have a question?
Can we write it like notation wise? It's like x to the negative 1, 2x to the negative 1/2.
1/2 x to the negative 1/2. Yeah. I wouldn't do that for what we're about to use it for. If you were using the shortcut, you'd get that, but you would want to rewrite it into this form in order to use it. Okay, so if we want to know what the slope of the graph, what is the slope of the graph at, I can read you guys, I promise. What is the slope of the graph of f? So of the function, square root of x, what is its slope at x equals to 1? That is the slope of the tangent line. So plugging 1 into f prime, we would get 1 over 2 times the square root of 1, which is 1/2. So we are able to say that the slope of the tangent line at x equals to 1 is 1/2. You could say the slope of f at x equals to 1 is 1/2. And we'll talk about that in a second, why that is. Or the instantaneous rate of change of f at x equals to 1 is 1/2. There's a lot of different ways you can describe that. We are going to come up with the equation of the tangent line. So that line that touches the curve at exactly x equals to 1 and nowhere else in that neighborhood. To come up with the equation of a line, well, we have a slope now, and then we have an x coordinate of a point. So why don't we find the y coordinate of that point, which would just be the square root of 1. So y is 1. And then we have a slope, we have a point. We can write the equation of a line in point slope form. So y minus 1 equals to 1/2 times x minus 1. Notice if we go to Desmos, where's my Desmos? So if I type in y equals, that not divided by, the square root of x, y minus 1 equals, this is kind of the nice thing about Desmos too, is you can just type in any form. Okay, so you can see the graph of the square root of x as well as the graph of the tangent line. If we zoom in, what does it look like is happening? If I zoom in even further to that 0.11, zoom in so much, what does it look like is happening to those two graphs? They're becoming the same. It looks like as we zoom in on that 0.11, that the graph, it almost looks like the graph is becoming linear of the function, the square root of x. So that's why we are able to say that the slope of the tangent line is the slope of the function at x equals to 1. That their rates of change or their instantaneous rates of change are the same. We can say that the function is locally linear at x equals to 1 because we can zoom in and the graph looks like a line. It looks like the line that's represented by the equation of our tangent line. Next time, we're going to talk about using our tangent line to make approximations of function values, tangent line approximations. Okay, let's do one more tangent line just for practice. So at x equals to 4, right, y would be equal to 2. Oh, we don't have the slope yet, right? We have our point now, we need our slope. So the slope of the tangent line at x equals to 4, we can just find f prime of 4 would be 1 over 2 root 4, which is 1/4. Okay, and then y minus 2 equals to 1/4 times x minus 4. That would be our equation of our tangent line at x equals to 4. Now you could, from there, you guys know how to find the different forms of the equation of the line, right? Like if this were a multiple choice question, you could just solve for y, right? Distribute, solve for y if all of the answers that were there were in slope-intercept form. Colin.
For C on like a test or practice, do we have to do it in point slope formula, or can we do it in?
No, it's just the I just think it's the fastest, right? Because otherwise you're having to do some extra algebra to solve for B. Right? Instead of just plug in, pop them in. Then you're having to plug in values, solve for B, and then write your equation. I don't know. Point slope form is your friend. Okay, what happens at x equals to 0? Well, first of all, y would be equal to 0, right? The square root of 0 is 0. Yeah. Yeah. But if we go and try and find f prime of 0, that would be 1 over 2 root 0, which is just 1 over 0. Uh-oh. Uh-oh. So you guys, what this means, since the derivative is undefined at x equals to 0, and we get a constant, so this is kind of the same, similar to like when you've just studied functions, like f prime, the derivative is its own function, which means there is a vertical tangent line at x equals to 0. This implies a vertical tangent line. Because the derivative is undefined, it means that f is not differentiable at x equals to 0. So because of this, we can also say f is not differentiable at x equals to 0. And there are different reasons why a function might not be differentiable at a point. This is one of them. If there is a vertical tangent line that exists at the point, there's a tangent line, but the function is still considered to be not differentiable because the derivative is undefined there. Okay. So this leads us to vertical tangent lines. So there's going to be a vertical tangent line if when you find f prime of c, right? We talked about that whenever I was reviewing, remember at the very end here, I talked about derivative at a point, plugging whatever c is. So if you were to, find f prime of c and you get positive or negative infinity, right? This is a limit. You guys know how to determine an infinite limit. We're going to look at this in a second with the previous example. If you get positive or negative infinity, it means that there is a vertical tangent line. So if you were to zoom in on the graph, and we'll do that with the square root of x, if you were to zoom in, it would look like the graph would turn into a vertical tangent line. I know, that's silly, huh, Felix?
Oh.
So silly. I know. Do you want to share what you're laughing about?
No, it's very funny.
Gotcha. You guys, the other day, I was giving a quiz in my pre-calc honors class, and I felt so bad. It was so inappropriate. I checked my phone because I had a text from my son's preschool teacher, and she had sent a picture of him like looking down with like you could see his lips sticking out. My husband had accidentally sent the wrong lunch with him, and he was really sad. He's 3, and it was like a lunch with like prosciutto and like mozzarella. Like it was just something like we had used the Tupperware that we usually use for his lunch. And it was so funny. I like couldn't help it. I was dying, cracking up, and I couldn't stop like through the entire quiz. And it was just really inappropriate. I'll show you guys the picture later. You'll think it's funny too. Well, maybe you will. Maybe you won't. I don't know. I thought it was really funny. Anywho, and this is being recorded. And sorry, Arjun, for that tangent. I went on a tangent. Yes. Okay, so using this definition of a vertical tangent line, so f prime of 0, because we're focusing in on x equals to 0, taking the limit as h approaches 0, right, of the square root of 0 plus h minus the square root of x, no, of 0, sorry, I'm replacing all the x's with 0, all over h. So if we look at what happens when we simplify that, we have the limit as h approaches 0 of, that's the same as h to the 1/2 over h, which simplifies to be, thinking exponent rules, what's that simplify to, you guys? 1 over h to the 1/2. Which, you know, if you were to use direct substitution there, you would get 1 over 0. And we already saw that with trying to evaluate the derivative at 0. Now, the thing is, the square root of x and there is a square root here. Is there, what happens to the left of 0 with like a square root? It doesn't exist. So this brings me to this bottom part here for the vertical tangent line. When the domain of f is the closed interval from A to B, you can extend the definition of vertical tangent lines to include the endpoints by considering continuity and limits from the right and from the left. Now, because we end up having this square root in here, in this simplified form, we're going to just think about taking the limit to the right. And if we do the test value, so if we were to pick a value directly to the right of 0, like 0.0001, and raise it to the 1/2, we would get a positive over a positive value, which means we could say that this limit fails to exist, but it fails to exist because it is approaching positive infinity. Therefore, there is a vertical tangent line, which we already discovered, at x equals to 0. So just kind of giving you an extra explanation for that. We knew there was a vertical tangent line from running into just plugging 0 into our derivative and getting a constant over 0. That indicates a vertical tangent line. But now we've used the more formal definition. Questions, you guys? Oh, so let's take a peek here. Let's get rid of that and zoom out. Well, x equals to 0. If we zoom in, right, you can see that the graph at 0, 0 looks like it is a vertical line. Okay, so let's find the derivative of h of x, which is the cube root of x, at x equals to 0. And you guys, I wouldn't make you use the limit definition to find the cube root. Like, this isn't one that we're going to find the derivative, because look at what happens. If you try and use just like find g prime by taking the limit, it's up to you if you want to write this down or not, because we're not going to do it. Yes. Probably shouldn't use H when I'm using the limit definition of the derivative. But you'd run into 0 over 0. Oh, what do we do from here? How do we rationalize the denominator or the numerator? How? But would that work? No, it is you multiply. It is fracton, but the version of 1 you have to multiply by is not just, well, it's actually not ratcon because you're not just multiplying by the conjugate. The version of 1 you have to multiply by is yucky to try to, no. Like no, we're not going to do it. So yucky, yeah. But pay attention to what this question is asking. It's saying find the derivative of cube root of x at 0. So h prime of 0, we can just plug in, I don't know why I put an extra on my m. So that would be the cube root of x plus 0 minus the cube. No, that's not it. 0 plus h minus the cube root of 0 all over h. So that's the limit as h approaches 0. Each of my limbs is looking very different today. So that would be the cube root, or h to the 1/3 over h, which would be 1 over h to the 2/3. Yeah. Okay, you'd get 1 over 0. But if you think about using test values, well, to the left of 0, if you plug in a negative, that like negative 0.00001, raising to the 2/3, it would be positive, right? Because you could think of that as being h to the 1/3 raised to the 2nd power, which would give you, or the reverse, right? So h squared raised to the 1/3, which either way, it would give you positive values, no matter what. So from both sides, you would get positive values, meaning that this limit would be equal to positive infinity. And therefore, there is a vertical tangent line at x equals to 0. And you can also say that h is not differentiable at x equals to 0. Was there a question? Sure. Up further? Like to here? Right there? Okay. Questions, you guys? Okay. Think about the graph. That's kind of obnoxious. Devin, can you close the door? Thank you. So let's think about the graph of y equals absolute value of x. Is today's schedule weird? What? What's going on today? When is that? Ugh. Wait, so what time are we out of this class? I support the assembly. I'm mad at myself because I didn't remember. Okay, we have 20 minutes. That's good. All right. Okay. Absolute value of x. what do we notice just looking at the graph? What do we notice about the slopes of the tangent lines? I'll pick a few points on here just to point out, right? 1, 2, how about 1, 2, -1, -2. We know, right? 1, 1 is a point, 2, 2 is a point, -1, 1, -2, 2. What do we notice about the slopes of the tangent lines to the curve at different points over its domain? Colin. Well, it is a curve. This is considered a curve. Is it though? Okay. What about 0? We don't. Have you guys watched Encanto? That's right. We don't talk about Bruno. Sorry. Okay. I have a 3-year-old, you guys. Encanto was all summer. So you guys, we can say, just looking at this graph, for x less than 0, the slope of the tangent line, right, f prime of x, would be equal to the left of 0. So -infinity to 0, the slope would be -1, right? It's a line, right, Brandon? It's a line with a slope of -1. Then we can say for x greater than 0, the slope of the tangent lines, f prime, would be equal to +1. And then we're like, when x is 0, I don't know. Where would my tangent line be? Would it like pass through here? Would it pass through here? Right? Would it pass through here? They're kind of infinitely many tangent lines that we could think about drawing at x equals to 0. That's weird. I wonder what that looks like with its derivative. So let's go ahead and find the derivative of the absolute value of x. And my hint here is our other form of absolute value of x, square root of x squared. So for f prime, no, I didn't use function notation. I'll call it y prime. Will be the limit as h approaches 0 of the difference quotient, but I'm using that other form of absolute value of x. So x plus h squared, the square root of x plus h squared, minus the square root of x squared, all over h. This is a retcon. So I'll multiply by the version of 1, which is the conjugate of the numerator over itself. Okay, so that'll end up being x plus h squared minus x squared. Oh my goodness. And then it like turns into a sledgehammer. Right? We have to multiply out that numerator. We need to uncover that h in the numerator that's going to cancel with the h in the denominator that was causing the 0 over 0. So x squared plus 2xh plus h squared minus x squared. And then looking at what will cancel x squareds, we can factor out an h to get that h to cancel. So that h will go away. One of those h's will go away. And then if we use direct substitution, let's see what happens. We get 2x plus 0 over the square root of x plus 0 squared. minus the square root of x squared. So simplifying that, that would be 2x over 2 root x squared, where those 2's can cancel. And then we can also rewrite the square root of x squared as absolute value of x. What would we run into, you guys? What is it? We ran into Jumpman. Whoop, whoop. Now our issue, so this makes sense, right? We ran into Jumpman, like the fact that our derivatives, like if we were to evaluate for x less than, right? The fact that when x was less than 0, we got -1 versus when x was greater than 0, we got +1, right? That was like another way to write Jumpman. Colin, you look skeptical right now. It is a curve. A line is a curve. As long as it's not a point, it's a curve. Isn't that crazy? The derivative of absolute value is Jumpman. That's cool. But we can see when we plug in 0 into our derivative, so if we evaluate y prime, and another way that I can write that is like y prime, I'll just write y prime of 0. We'd get 0 over 0. We'd get an indeterminate form. That indicates that it's not a vertical tangent line. Not a vertical tangent line. But it doesn't exist, right? This is undefined because we've run into indeterminate form. So absolute value of x is not differentiable. What? Yeah. And I went forward with it being like it was plus. It was just a whoopsies. So y equals to absolute value of x is not differentiable at x equals to 0. We can see that from looking at its graph. There are infinitely many tangent lines that we could think about drawing to the curve at x equals to 0. To that sharp corner, to the graph at x equals to 0. And therefore f is not, or y equals to absolute value of x is not differentiable. But this leads us into our discussion about differentiability. And in order to talk about differentiability at a point, it can be helpful to use this alternative form of the derivative. And to kind of go back to our picture of like this, if we were to, let me draw just a curve real fast. Okay, so let's say that we have the interval x to c. Or you could do c to x, it doesn't matter. Where this point would be x comma f of x. This point would be c comma f of c. right? Secant line. Ooh. If we wanted to find the slope of the tangent line at C, comma, f of C, couldn't we think about dragging this point closer and closer and closer and closer and closer to C, comma, f of C? Where you could think about making X approach C. Doesn't that make sense, right? And then average rate of change for that picture would be f of C minus f of X, right? F of C minus f of X over C minus X, or they did it the other way, huh? It doesn't matter. They have it switched here. To match them, I'll switch it. But remember, that order doesn't matter. So I'll change this just to match. As long as you're consistent, right? So if we thought that would represent average rate of change, slope of the secant line. But then if we think about taking the limit as X approaches C, that would end up giving us the slope of the tangent line, which is the derivative at X equals to C. Well, here's the thing. If this is a two-sided limit, for this limit to exist, the one-sided limits have to exist. So it's already written out. So I'm gonna go back up here. So for that limit to exist, the one-sided limits would have to both exist and be equal to each other, just like for any other two-sided limit to exist. Colin. Yes, you can. So f is differentiable on the closed interval when it's differentiable on the open interval from A to B, and when the derivative from the right of A and the derivative from the left at B both exist. So when a function is not continuous at X equals to C, it won't be differentiable. But we have seen that a function can be continuous, but not differentiable at a point. We just looked at a couple examples. We're going to examine a couple more examples, even ones that we've already looked at, but from this new perspective. So just because a function is continuous does not mean it's differentiable. However, for a function to be differentiable, it better be continuous. So differentiability implies continuity, but continuity does not imply differentiability, and that's important. If you are given information about a function, like you are given that it is differentiable over an interval or at a point, you may assume continuity, but not the other way around. So we already looked, right? We looked at this function. We know that it's continuous at X equals to 0, but let's look at it from the perspective of this alternative definition of the derivative. So if we were to think about taking the limit as X approaches 0 of absolute value of X minus absolute value of 0 over X minus 0, we end up running into Jumpman again. Just from a limit perspective, you guys know this doesn't exist. This limit doesn't exist. Thinking about the limit from the left and the right. Jumpman. Okay, if we thought about taking the limit as X approaches 0 from the left of Jumpman, we would get -1, which does not equal to the limit as X approaches 0 from the right of Jumpman. That's equal to +1. So therefore, the limit as X approaches 0 of Jumpman is dne And you can say that f is not so therefore f is not differentiable at x equals to 0. This next one is going to be an example of where function will be differentiable at the point, because I want you to see what it looks like whenever it is. So using this alternative form of the derivative, we're going to prove that f is differentiable at -1, meaning if you evaluate its derivative, you get a real number. So f prime of -1 would be the limit as x approaches -1 of 1 over x minus 2 minus 1 over -1 minus 2 all over x minus -1. So to simplify that before I do anything else, that's x minus 1 over x minus 2. That'll end up being plus 1/3 over x plus 1. Oh, and the limit as x approaches -1, not 1. What happens if we plug in -1? 0 over 0. So we have some work to do. We're going to multiply by the least common multiple of those denominators, which would be 3 times x minus 2 over itself. The x minus 2's would cancel. We'd have 3. And then plus x minus 2. And then that numerator would cancel with the x plus 1. Drawing a line to continue my work. So I'm taking the limit as x approaches -1 of 1 over 3 times x minus 2. And when I use direct substitution, that gives me -1/9. That's the slope of the secant line. Not the secant line, that's the slope of the tangent line at x equals to -1. We got a slope of the tangent line. That means that f is differentiable. It would not be, and looking at that limit, it would not be differentiable at 2, but 2 wouldn't even be in the domain of f, and therefore f wouldn't be differentiable there. All right, you guys, we just had one more. We'll finish this last example next time. Do your best shot at the 2.1 homework. I'm going to try and get my solutions posted today so you guys can reference that. Email me if you need anything before Tuesday. We're going to continue on with 2.1 on Tuesday. Yeah, thanks for that. Bye. You too.